This is a supplementary lecture to the Week 4 slides in the Executive Black Belt course, and this covers ANOVA and Chi-square, slides 143 to 176 in your binder. And you'll notice that we're covering ANOVA and Chi-square, not the analysis of means. There's two reasons for that. One is the analysis of means is only available in Minitab, not Excel statistics, and that, well, it's available in other packages as well. But of the ones that we're typically using, it's only available in Minitab. And the second is that it's probably the least important of these three techniques. Let's just teach you one for each of the specific cases that we have and move on. That way you'll have a clear way to move forward on each of these. The situation that we're going to cover is the following. Let's consider the first case where we have an output Y and an input X, or a driver X, and our output is a number and our input is a cat. So we've discussed plenty of examples like this. In fact, this is probably the most common that we run into. An output might be the cycle time that it takes to complete a process, the time that it takes me to discharge a patient, the time that it takes me to deliver a meal to your table at a restaurant, the time that it takes me to enroll you in a service at a healthcare insurer, the time that it takes to manufacture a part in a manufacturing plant, the time that it takes to move goods from one place to another in material handling situation. So plenty of examples like that. And my X, my driver, might be, for example, in the material handling, it might be what type of forklift do I use, right? Or which driver do I use? If it's in the discharge of a patient, which doctor's patient was it? That might be a categorical variable that we want to break apart. Now, up till now, we've only considered two cases, examples of X where X has two categories, like, for example, driving speed versus gender, or the answer to perhaps a yes or no question, is the person above 45 years of age or not? But now we want to extend that. ANOVA helps us extend our questions beyond that, both for means and for variances. ANOVA generally is a technique that, it stands for analysis of variance, but it generally refers to looking at differences between means, which is confusing to most folks. It just happens to be the way that, unfortunately, Sir Ronald Fisher named it, and it was because he got at the differences of means by looking at a table of variances. So he called it analysis of variance. Unfortunate name, but that's, in effect, what it does. So we're going to look at that. That's the ANOVA. So this is going to be the ANOVA setting right here. And the chi-squared setting is just as you would think. It extends, so this is means for more than two groups. And the chi-squared setting is going to extend proportions. So that will be when we have an output Y and input X, where the input X is a cat, but also the output Y is a cat. Now, it doesn't have to, and often with these situations, it's not so much input and output, it's really just two variables. So, for example, an example that we'll cover is I want to estimate if there are differences by city, by where I live, either in the city or the country, in how I respond to a customer survey. I might, in whether I agree to a tax abatement. It may be, yes, I agree with this. It may be, I know I disagree with it. And it may be, I'm neutral about it. So there's three categories of one of these things. In this case, it's the output. So I might want to break up a proportion by three different categories. Perhaps a more straightforward example might be, I want to look at people who, I might ask somebody, do you like several soft drinks? I might give them a sample of Pepsi, I might give them a sample of Coke, I might give them a sample of Dr. Pepper, I might give them a sample of 7-Up. And I want to know if those proportions of, if the proportions of people who like these different soft drinks, like them in different proportions. In other words, if the proportion of people who like Pepsi is different from that of Coke or of 7-Up and so forth. So I might have 4 or 5 categories. All right, and that's the chi-square. Now, it's sort of like good news, bad news, because as we'll find out, yeah, ANOVA lets us compare multiple things at once, but it's only helpful if, in some ways, if we do find that there are differences, in other words, that it's significant, if our particular variable is a significant driver of the output, we're going to have to do more examination anyway. So we'll show you how to do that, okay? So those are called either post hoc tests or multiple comparisons. We'll show you how to do that, okay? And that essentially says we do an ANOVA first, and then we have some follow-up to do. All right, let's cover the ANOVA first, because I think that that's the more common of the two, and it's the one that people will ask about more often too. So the example that we're giving is wait times. You can think of it as wait times at either a help desk or something like that. I like to think of it as when I bought a computer, I might have I might call a helpline, and I might have several different options of service types. So, for example, wait time is a number, right? And service type is a category. But when I call, I might have that first thing on the menu be, are you calling for a billing inquiry? Are you calling for a technical question? Are you calling to start a service with us? This could certainly work in this could certainly work at a healthcare company, call center, something like that. The idea, if I have wait times, people wait differing amounts of time for different services that I offer. Okay, so I want to see if that's a driver, and as usual, we draw our PGA, and the P ought to be, I wonder if service type is a driver of wait times. Let's make a plot of that right away. We learned that last time that the box plot is our plot of choice, so we're going to go ahead and do that. Let me first do the example in Excel Stats. Then I'm going to do the example in Minitab. So in Excel Stats, let's first get it open. Here's wait times. Okay, that was easy enough. I've got wait times up, and I've got to open up Excel Stats. I'm doing it in Excel Stats 2003. Very, very similar to 2007. First thing to do is select. Making sure I'm recording here. Okay, first thing to do is select. And then we'll go one num, one cat. Now this is kind of instructive. This is sometimes what happens if you don't have, now Excel Stats is not smart enough to know which order you put your spreadsheet in. So it's nice enough to label at the top, hey, this first one's supposed to be a num and the second one's supposed to be a cat. We've got them mixed up here. No bother, we just use the drop-down menu to switch those up. And there we go. Now we're in good shape, or better shape anyway. Let's go to the Summaries tab. Just a quick glance at this. It certainly does look like the means are different. I just looked at the numbers here. I know that's a no-no. We should be looking at plots first. But okay, let's come over and look at the, let's take a look at the box plots. And there we have it. It certainly does look to me. Let's apply the first. Remember, the idea was we applied two tests. The first was whenever we have a numerical output, like we do here, we have a numerical output. We're going to apply two tests. Let's try that again. We're going to apply two tests. The UFO test, which is probably the most important, which is I'm pretending these are UFOs, and if I see some hovering between any of the two groups, I'm going to say means might be different. Well, here it certainly does look like there's a little bit of hovering. It looks like technical is hovering above billing and service enrollment. It looks like these are about at the same level. Maybe one is a little bit higher than the other, but they're about the same. So I'm going to test the means. Maybe the means are different. Now, in ANOVA, the test, the hypothesis test, we usually don't write it out. At least I don't usually write it out. It is given in the book on slide 160. However, and so I'm going to write it out here. This would be essentially this: mu for technical is equal to the null hypothesis would be mu technical is equal to mu billing is equal to mu service enrollment, SE, versus the alternative, at least one pair is different. Okay? fairly vague thing. So let me be blunt about this. Suppose that we reject the null. You remember when I was saying that the hypothesis test is good for telling you what's not true. In effect, it tells you that the null is not true. Here's a good case in point. It tells me that the null is not true. If that's not true, what does that really say? Well, not a heck of a lot, right? It says at least one pair is different. It's still up to me to find which one are the different pairs. That's why it's good to look at the data first, because I might do some testing after I find out that I reject the null, if I indeed do, that I need to go further on. Okay, so that's my hypothesis test. Now let's go ahead and run that hypothesis test. I can do that for ANOVA in Excel Stats. I go to Tests of N categories. Don't worry about the fixed and random effects. So you can just leave them on fixed effects, and for now. And if we come down here, it says, there it is, all population means of wait time are equal versus not all of them are equal. And it says my p-value is 0.014. There it is, which says that certainly p is less than 0.05. Let's go back to the tail of the tape. Here we found that p is less than 0.05, right? Because 0.0014 is certainly less than that. So therefore, I reject the null. In favor of the alternative. So at least one pair is different. Whoopee. Okay, now it's up to me to figure out which pair and to make different, or which pairs and to make which estimates. So I'm going to do multiple comparisons. I'm now going to compare a few things. Now I guess I'll use the black marker now. I'm going to essentially compare mu t with mu b, and I'm going to compare mu t with mu, I guess I called it SE, service enrollment, and I'm going to compare mu b with mu service enrollment. Okay, so I'm going to do all three of those. I'll do them all in their gory detail, and then I'll show you very quickly how you can make a quick comparison. Let me show you how you can make a quick, actually let me do it the opposite. I'll show you how you can do a quick comparison, which should give you an idea of what's important anyway. If you go to the Summaries tab and go down, you'll see these comparison of means. If you stick it on confidence intervals, you should be able to tell pretty quickly that technical is different from billing because these two confidence intervals don't overlap. However, it's also different from service enrollment. We would expect the p-value to be even bigger for that. And we would expect maybe billing and service enrollment don't agree with each other. Now, if you're a statistician and you're seeing this, you're saying, oh, Mark, come on, you're making a rookie mistake here. You actually are looking at a different comparison. The short answer is yes, true, but what I'm looking at here is conservative. So the point is that if we see non-overlap here, I can almost guarantee you, that when we do the individual t-tests, that we'll find differences in the technical versus billing, technical versus service enrollment, and that. Here we're looking at all three at once, which I think is a powerful view, actually. And although it's a little conservative, that is not quite as powerful as looking at them individually. It will give you a pretty good picture. You can tell at a glance. Let's see if that's actually true. So to do the 2x2s, remember there are three of them in this case. Let's go over to here. First, let's compare technical and billing. We have a non-equality, and there it is. We find that that is indeed different. They're significantly different. So I'm just going to go ahead and circle that one. So I'll circle technical and billing here. That's, whoops, we found that that was not equal, right? That's significant. All right, let's go to the next one, technical and service enrollment. Notice how that just has a drop-down menu. It's kind of cool. Yeah, there it is. That's very significant. So again, I'll circle that one. We found that those were not equal. And finally, billing and service enrollment. And nope, in this case, the p-value is bigger than 0.05. So we do not reject the null. So in this case, we're just going to leave that equality, and it's not something we're going to hang our hat on. So in fact, in this case, our intuition and the picture that we used before was correct, that there are differences between technical and billing. There are differences between technical and service enrollment, but no real difference in means between billing and service enrollment. At least there's not enough evidence that we can use to say that. That's Excel stats. Let me show you how to do that in Minitab. Minitab's a little bit more complex, but as you'll see, by the way, I mentioned that if you were going to test variances, which we'll do in just a moment, Minitab is the only way to go. Excel stats doesn't do it. Minitab does. All right. So let's go ahead and get the data into Minitab, and I'll show you how to do this in Minitab. Okay, to do it in Minitab, here's my data right here. You can see it's the same. We'll go to Stat, ANOVA, one way. Wow, lots of ANOVAs. Let's just choose the first one. Aha, look at that one, test for equal variances. We'll be going there soon. Our response is wait time, and our factor is service type. We can make multiple comparisons if we want, and I'll show you that in just a moment, or maybe I'll show you that in just a moment. And if we want, we can make plots. Let's make box plots. There's my box plot. So let's see, Minitab can do box plots too. It's kind of good. All right, now let's go to the ANOVA. And here's what Minitab does for the ANOVA. You'll see that service type, it gives this table. Remember I said something about the table? Yeah, this is called the analysis of variance table, and we'll see this later when we talk about regression. The important thing to pull from this table right now is this p-value, and that says that service type is a significant factor in determining wait time. There it is. The p-value is certainly smaller than 0.01, so that's the equivalent of our first test, which was, oops, now it's missing a few. Oh, yes, I understand why. Because remember, this was gray before. This was all of them are equal versus at least one pair is different. So, again, we circled the same one. Now it's a ghost, though. Let me fix that. All right, this is H naught, which would be mu T, is equal to mu B, is equal to mu SE, versus HA. At least one is different, is diff. Okay? That's what that is. Now, the interesting thing, Minitab will allow us to do a few of these tests very quickly, but it does it in kind of a crazy way. So I'll show it to you, but you're probably not going to like it. Okay, here's our Minitab's overall confidence intervals, and you can see there's overlap with these two, which are billing and service enrollment, no overlap with technical. So that gives us the same answer that we had before. Now let's see how Minitab does all the tests at once. And to do that, you can do a Control-E in Minitab and go to multiple comparisons. As is usual, Minitab gives you 10 different things, actually only 4. We're going to choose Tukey. I actually had a class from Dr. Shu. He was a professor at Ohio State. Sorry, Dr. Shu, we're not going to use your multiple comparisons. We're going to use John Tukey's. Okay, let's go ahead and click. Okie dokie. Oh yeah, I forgot about our plot. It's an interesting plot. Let's move on by for a moment. And like I said, you're probably not going to like this. It does have a nice little, this is Minitab 16. This has been an added feature. Minitab has this added grouping right away, so it does some grouping of all the different types. In this case, it says, oops, sorry. There we are. In this case, it says technical and billing. Technical is in a group all by its own, just as we saw up here in the confidence intervals. All right, so now what it does is it does all the multiple comparisons. It does it slightly different than what we had before, but basically the same. Gives us the same result, or it gives us a very, very similar result. For those who have an eagle eye, you'll notice that we have a 98.07 instead of 95% confidence intervals. I'm going to sweep that one under the rug. If anybody would like to know, please call or contact me directly, and I'll tell you all about overall alpha level and lots of fun stuff around there. For now, I think that difference is so small, let's not worry about it too much. So what this does, what Minitab does now, is it compares all of the things together. The first one it does right here is it says service type equals billing subtracted from. So the first one says billing subtracted from service enrollment, billing subtracted from technical. And think about it this way, what Minitab's really doing is it's drawing a line right here at 0. It draws a better line than I do. And it tries to check to see if the confidence intervals overlap. If they overlap, we can't say they're different. If they don't overlap, we can say they're different. So this is the comparison of technical with billing. Does not overlap, so we said, again, same conclusion, technical and billing are different. Here it says service enrollment and billing. They do overlap 0. Therefore, they're not different. I'm sorry, therefore, we cannot say that they're different. So that's that one. And here's the third one, which is a comparison between service enrollment and technical. And there's my, I know I'm writing over this, but there's my confidence interval. There's the start of my confidence interval, way away from 0. So again, they are different, and that's the same conclusion that we came up with before. A little bit simpler and a little bit more obvious in Excel stats, I think. So that's it. That's ANOVA in a nutshell. And we covered it in Excel stats and Minitab. All right, one last thing I wanted to point out is, suppose when you do the box plot, you also wanted to, we'll do the box plot with groups here, you also wanted to, I keep having this signature thing come up, not sure exactly what that is, but it's kind of annoying. When this comes up, we might also apply the birthday present test, right? In the birthday present test, what we do is we look at the sizes of the boxes, and that's for determining whether or not we want to investigate whether the variances are the same. Well, here, I probably wouldn't be all that interested in investigating it, but you might say, sure, looks like maybe service enrollment is a little more variant than the others. So let's go ahead and test it and see if that's a figment of our imagination or just a small sample, or it's really true. So let's go ahead and find that out. To do that, we can go to Stat ANOVA, Test of Equal Variances, and this will compare more than 2. Remember, in the basic statistics, we were able to compare 2 variances, but here we'll be able to compare more than that. So again, Stat ANOVA, Test for Equal Variances. We'll pick our response is wait time, and our factor is service type. We can put a title on the plot if we want, but that's okay. Go ahead and click OK. And it gives us a nice picture, sort of. Basically, these are all confidence intervals for the variance, or for the standard deviation. And in fact, they are 95% Bonferroni confidence intervals. In case you really wanted to impress your friends, you can say that they're Bonferroni confidence intervals. I'm sure that'll really impress them. Maybe not the way you hope to impress your friends. Okay, anyway. The equivalent of the F-test, when we have more than 2 variances, is called Bartlett's test. So this holds for normal distributions. Levine's test is just as it was before. This holds for all distributions. And we can see by these p-values, very little evidence that there is any difference between standard deviations. In fact, there's really no evidence that there's a difference between standard deviations. So if we go back to our original plot, which was, let me see if I can bring that up again. Here's my box plot. Yeah, if we go back to this original plot, the differences that we're seeing in the sizes of the boxes are really due entirely just to sampling. We can't go any further than that. So that's our test of equal variances. Not too interesting, and not too common, by the way. All right, so a recap on ANOVA. And a recap on ANOVA for our example in wait times is it certainly looked like the means were different. And in fact, we thought that maybe mu technical was greater than others. and we tested it. It was true. It's true. And so we would be left with doing something about it. So it might be things like, well, if you have a technical question, you're given a different expectation about how long you're going to have to wait, or we'll staff up on more people who can allow technical, or we'll cross-train people. You know, solutions that matter for those things. But again, now that we've established that that the means are statistically different, we can do something about it, and it makes sense to do something about it. All right, ANOVA. Test differences in means when you have more than 2 categories. That's it. Okay, let's move on to the chi-squared test. And chi-squared test helps us when we have proportions, but we have a y as a cat and an x as a cat. And one of these, either one, it doesn't really even matter if it's input or output, that they're both cat, and one or more of them has more than 2 categories. Okay? So that's it. The example that we are going to do is our y is response from a survey on the tax abatement, and our x is where you live, city or country. So in this case, this is a cat, and this is also a cat. We're interested in looking at if there are differences between one or more of these categories. Well, let's start with our PGA. Okay, we're going to start by doing this one in Excel Stats. And I'm actually going to do 2 examples, one where the data are already summarized. It happens a lot when you have categorical data that the data are already summarized. In this example, the data are not summarized. They're what we call raw data. So let's take a look at that. I'm not going to save the changes to time. And I'm going to get out of the one num. And I don't need my box plots anymore. See you later, box plots. Okay. Okay, so if I look at, this is found in tax statement, and it's the example that is given on slide 166 in your book. So let's go ahead and do this. If we pick the response of response and the type as type, that's our city, right? Our response is agree, disagree, or neutral, and our type is either city or rural. Let's first of all make a plot of that. So we've got 2 cat. Here's a table of that. Tables are great, but they're not all that interesting. They're hard to really discern data from. Plots are way better. Let's take a look at this. Okay, so here's basically what we want to see. We want to see, are these profiles different for rural and city? Well, to me, they certainly look very, very, very different. But the question is this real, or is it a figment of our imagination? Another way of looking at this, and I often like this when I have 2 cat variables. Sometimes one view is better than another one. And here's the one that, in this case, I think works better. If there were no differences between any of these groups, in other words, if we just got 30%, 30%, 30%, 33%, 33%, 33%, all the way across, and that there was no preference for agree and disagree, it would be flat. But in this case, it certainly does not look as if it's flat, right? At least not to me. To me, it really does look like there's a difference in agreement and in disagreement and in neutral when we're talking about city versus rural people. Okay, same way with this. It doesn't look like it's flat all the way across, both for city and rural. Either way you look at it, that's basically what we're talking about. Okay, to do that right away, in Excel Stats, you simply click on Tests R by C, and that gives you the chi-squared test. It even gives you the Pearson chi-squared test. Carl Pearson is a giant in early statistics. He's the guy who invented the correlation coefficient, as well as the chi-squared test and a number of other things, a real giant in statistics. And certainly it says here, for example, that we have very high evidence that there is a difference. Incidentally, I'm going to try this. The hypothesis test, and we'll write this out. I'm going to erase that. In a chi-square test is equally interesting as in the ANOVA. In other words, just because you find something that the chi-squared gives you something significant doesn't mean that you've ended the problem. You still have to dig deeper. So in this case, our null hypothesis is pi 1 is equal to pi 2 is equal to pi 3. The proportions are the same for neutral and for disagree and for agree, versus at least one pair is different. They're all same for city and rural. Okay, that's my alternative, and this just tells me that I reject that null. They're not all equal. At least one of these pairs is different. So let's go ahead and you know what's coming next. The next thing is, hey, let's do these tests one by one. I have a shortcut, and a shortcut I believe you will like. We come back to here. We can actually click on confidence intervals, and this is going to be easier if we swap the variables. We'll click on confidence intervals. If we leave it at 95, we're actually doing a 0.05 test, just like we did before. And we can look at these pairs and see if they overlap or don't. We can see at a glance, for example, that the agree confidence intervals do not overlap. Therefore, we know that the differences between proportions of people who agree and who disagree, who agree are different in rural and city. Okay? We also know that the proportions of people who disagree are different from rural and city. And finally, we know that the amount of neutrals, the proportion of neutrals, we're not going to reject the null in this case. We're going to find that we don't have enough evidence to reject. Okay, now this is just conjecture, and remember that my statistics friends are rolling their eyes because this isn't quite true, but it's darn close. I'm going to back it up by doing the individual tests, but, by doing the individual tests, but you can see, I mean, this is a nice picture that tells you right away what's significant and what's not. To a high degree, that's true. All right, first of all, we want to do, we're comparing rural and city for agree. There it is right there. Certainly, those are different. P-value of less than 1 or less than 0.05, absolutely, they're different. Let's look at the disagree. Oh yeah, look at that. 5 zeros in front of that 1. That's very small, so the difference between disagrees in rural and city proportions, very significant. And neutral, it's getting there, but no, we cannot say that they are different. That's it. That's it, folks. Not too super interesting, but you know what we can really say is that the proportion, if we're comparing city v. rural, the proportion who agree is different in the city versus rural. That's different. We can say that the proportion who disagree in the city differs from that of rural. But we can't say that for neutral. The amount of neutrals are the same, are really different in city versus rural. So it allows us to go in and make real, take a real substantial look at this. City versus rural really is a driver of that result. It's really driving the results. It's really a key explanation of why we're getting the results that we get. We found it to be statistically significant by doing that chi-square test. All right, let's do this in Minitab. Minitab is good and bad with chi-square. So here's the bad part. We'll show you the bad part first. Let's go into Minitab, And very quickly, I'll show you the bad part first. Get that out of the way. Okay. Now I popped it into Minitab. In Minitab, to do a chi-square test, it's for some reason in tables. So you go to Stat, Tables, Cross-Tabulation in chi-square. Now we're going here because we have raw data. It'll turn out that we go to the two-way table in the worksheet when we have summarized data. And I'll show you how that looks in just a moment. Let's do this one first. Cross-tab and chi-square. Whoops. Okay, so the first thing is we'll just put in the row and the column. And this is just how the table layout is going to look. It's not how it is in Minitab. We just want to put in our variables. One row, one column. Click on chi-square, and we're going to ask it to do the chi-square analysis. I'm going to also click on something. Yeah, I'll click on this, and then we'll come back to expected cell counts in just a moment. Give us some insight to the test. Well, here it is in all its glory and really super highly interesting. You can see it summarizes this just as Excel Stats did, and it gives you some stuff about the Pearson chi-squared. There's our p-value. It also does a different test called the likelihood ratio chi-square. In this case, all roads lead to Rome. Pick the first one. That's the most usual. And again, it tells us yes, there's a difference between these proportions, and we need to dig into where those are. So, if you're in Minitab, the picture is not so easy to make, right? What is the picture? How did we get here? Excel Stats nicely does that picture of the clustered bar chart. However, there is a way in Minitab to get there. Hit Control-E, which brings you back to the last thing you did. And remember I said I was going to go back into expected cell counts. Let's go ahead and click on this. This is one way to kind of ascertain where most of the smoke is coming from. So now in the table, before we just had the table of numbers, but now in the table it says how many do we actually expect in each cell of this table if all things were equal, right? So if all things were equal, notice that we overall had 46 city folk and 37 rural folk. I'm trying to be extra folksy, I guess, in my dialect. That with those particular numbers, if it were split, if we got the split that we got overall, if we looked at this overall split, we would have gotten 12, roughly, almost 13 in the city that agree, 10 in the country that agree, roughly. And for the disagree, we would have gotten these numbers. Now you can see that, for example, here, those are big differences. See, 6 from 12, 17 from 10. That's a pretty big difference. Here's a huge difference, 32 from 22, 8 from 17. So that's a bigger difference. And finally, in neutral, you can see it's not as big, 8 to 11, 12 to basically 9. So where the differences are likely to lie are in the disagree and in the agree portions of that table. All right? That should give you some insight. Now, the way that this is really actually working is this I'm going to take out the expected cell counts and add each cell's contribution to the chi-squared statistic. So this thing right here where it says 19.717, whatever that means, we're going to see which cells are the biggest in terms of contributors, and it tells us, again, where most of the smoke is coming from. And there you can see that the big ones are in the agree, city and rural, the disagree, city and rural, but the neutral are much smaller. If you add all those up, you'll get 19.717. If you add up 3.571, 4.440, all that, you'll get 19.717. If you didn't want to know that and you just wanted to know the p-value, well, sorry about that. I told you a little more statistics than you needed to know. Okay, that's all I want to show you for this one. Let's do one more example, and I think you'll see why. I'm going to do the example that you will eventually get in an assignment. It's on 174, and it's called Auditors. Close this up. The reason I'm showing this to you is because it's hard to do this in Excel stats. You can do it, and I'll tell you how to do it, but it's hard to do. So very often you'll have tables of numbers like this. Somebody has already summarized this. And the setting here, let's just do the setting in this. Okay, great. I'm going to erase all of this. Yep. So my setting in this case is I seeded a bunch of errors. I seeded 120 errors. 120 errors were seeded into some files. And I wanted to test, to check the checkers. We'll be looking at things like this in measurement systems analysis. I wanted to check my auditors to see how many of those they would find. So I had 3 auditors, imaginatively named Auditor 1, A1, A2, A3. I gave them each 40. They each got 40. Right? 40 plus 40 plus 40 is 120. And I recorded how many they found. So that's given here in the table. So for example, of the 40 that Auditor 1 was given, he found 37 errors. And of Auditor 2, he found 31. And Auditor 3, he found 36. Now the question I would have, now notice that the data are not raw. If I wanted to put the data into raw, I could certainly do that. I could certainly create columns that were like Auditor 1, how many did he have? 37 yeses, 3 no's. Auditor 2, 31 yeses, 9 no's. Auditor 3, 36 yeses, 4 no's. I could create that data, right, and then do the whole thing in Excel stats. That would be fine. I could do that. But if you don't want to go through that thing and you just want to ask the question, hey, do you think maybe I should apply some tough love to Auditor 2? Do I really have enough evidence? I think many people would say, absolutely. You know, we gave 40 of these out, and look at the difference. I mean, let's look at the error rate. This guy missed 9 out of 40. So what is that percentage-wise? Equals, let's see, this divided by 40. And that's 22%. You know, I mean, it looks huge. This guy's 10%. And let me just put on the percents. 8%, 23%, and 10%. Wow, I mean, it looks like Auditor 2 is horrible at catching these. Now, if you've been following this class, you should know that a theme is that we can't simply trust the fact that they are different. We have to ask the question, do we have enough of a sample size to really say that that difference is significant? So let's see. And that's what we're going to use our chi-square test to figure out. So to do this, we'll pump it into Minitab. And here Minitab is going to be pretty helpful because it's hard to do in Excel stats. All right. So if we go into if we go into Minitab, we can do this by looking at stat, tables, and remember last time I told you if you don't have it tabulated, you go to crosstab. If you already have it summarized, you go to chi-square test, two-way table and worksheet. So we can do that. And in this case, looks like I already did it. We can select found and not found. And it doesn't matter if we do it this way or we format the table the other way, like put auditors on the top, auditor 1, 2, 3, and then label it found and not found. We do have to do both, have the found and not found. Okay, notice we can do that, and that's important. Proportions, you can do that, right? Proportion yes, proportion no. Okay. All right, and let's click the okie dokie button, and there we have it. It turns out that we get a P of 0.107, which is very interesting. It says that we cannot reject the null, that these proportions are different. So even though they look very different by auditor, right, it certainly, to me, when we looked at it, it certainly looked like, if we were writing down this hypothesis test, proportion for auditor 1 is equal to proportion of auditor 2 is equal to proportion of auditor 3. It certainly looked like we were going to say, no way, at least one is different. At least one is different. It certainly looked like we were going to reject that null, but there it is, P of 0.107. We cannot reject the null. So effectively, here's one where we're not really circling this. I'll circle this with a dotted line. I wouldn't say that, hey, they're all equal, but we certainly don't have enough evidence to say that they're different. I think that's probably very non-intuitive for most of you. If you're looking at, most people would say, well, 23%'s got to be different than 8. Not if you don't collect a lot of data, it isn't. And it turns out that there's two things that we ought to take from this. One is, in a chi-squared test, what we try to do is there's a rule of thumb of wanting to find in each of these cells at least 5. That, in other words, if you sample enough so that you get at least 5 in each one of the cells, you have a fighting chance of finding differences. That's one thing. But the second thing to take away is, remember, categorical data not as powerful as numerical data. If you had this many data points and it was numerical data and you had real differences, you would have found something, guaranteed, or almost guaranteed. But with categorical data, it's not that powerful. You need a lot of it to be able to see statistically. Okay? So those are the two things I wanted to show you. I stopped this a little bit and I decided to show you what it was going to look like in Excel stats if you wanted to create the raw data from this. It would take a little bit of time, but this is basically what it looked like. It would look like you'd have to create a column that labels the auditor. So if you look, I'm going to scroll down here. It'll go from A1, A2, A3. There it is right there. And then to put in the right ones and zeros, for one for yes, I found that error, or not, I'm simply filling in the data right here. So I'll have 37 ones and 3 zeros for auditor 1, 31 ones and 9 zeros for auditor 2, and so forth. If you look at that, that's what I've done right here. I'm just going to scroll up. There's my zeros for A2. There's my zeros for A3. See, there's only 3 of them for for A1. And now we can go ahead and do Excel statistics. We've got 2 cat. And for those of you who really like the pictures, there it is right there. I want to make sure that I got the thing right. There it is. There's my table. So I did get it right. And here's what we found. You can see that there's not, that there really aren't differences. Let me do this comparison. Yeah. So here is whether we found them or not. This is the proportion found. Yeah, it's not really differing. In this, see, it overlaps. This is the proportion of not found. It certainly looks like it's different for auditor 2, but it's not quite different enough. See, it is higher, but it's not quite different enough to be a different. Here's our chi-square test. Remember, it was 0.11 in Minitab. There it is, 0.11 in Excel statistics as well. So all roads lead to Rome, and we can even go here and look at the comparisons of each of them. Now, if we wanted to do it the other way around, which looks to me like the way I would want to do it, like compare auditor 1, 2, and 3 for found and not found, we can go back to here, I think, and just swap the variables. Could be wrong. No, we've got to actually go to the data and description and switch the order around. See, and that puts here found 0. So let's look at the not found. Let's compare auditor 1 and 2. Oh, I see. It's because these are not numerical values. We need numbers in order to do this. Let's go back and switch it. Do the old switcheroo. Okay. I think we'll just stop here with the p-value, and we'll look at the summaries. Again, I think that this tells the whole story. These are the proportion of founds. Yeah, it looks like it's lower, but not lower enough to say it's real different. And here, not quite low enough to say that it's really different. Certainly not at the 5% level. So there you have it. Chi-squared test and ANOVA. So let's finish up by having just a short summary of this. So chi-squared test, in the example that we did, we found that it was significant for the first one, and it was non-significant in the auditor case. Okay, so we've covered the ANOVA and chi-squared. Again, this is the stuff that's on 143 to 176 in your binder. This is extending when you have more than 2 categories. ANOVA rules for when you have a number output, a category input. Chi-squared works really well when you have a category output, category input. Remember, these particular techniques are helpful for being able to talk to other black belts and things like that. They're helpful once you get to learn to master them, but if you have trouble with them, you can always fall back on the 2 proportion, 2 sample t, and just be sparing about which tests you use by looking at the plots first. That's perhaps the best advice I can give you, is that if you know the questions and comparisons that you want to make by looking at the plots first, you can judiciously just use the 2 sample t test if you have 1 num, 1 cat, and the 2 proportions tests. Do it twice or 3 times if you have cat. Okay? All right, well, I hope you enjoyed this lecture, and we'll see you next time.